Assalamu alaikum. Is my voice clear? Okay. Okay, so let's start without any delays. So those who want to join can join later and then watch this part. Okay, so the question is, you can read the statement. Whatever frequency 3.6 hertz is generated in a ripple tank. Figure 5.1 is a scale diagram that shows the wavefront traveling from deep water to shallow water in the ripple tank. A length of 1 centimeter on the diagram represents 8 centimeters in the ripple tank. Now, one of the key points about this question is that they've told us that this is uh, a scale diagram. A scale diagram means these values, these distances on the diagram are of importance. Like it is to some scale, like you can use these values. And then in the next part, they've told us a scale. So first, they tell us that it's a scale diagram, and next, they tell us the scaling. They tell that a length of 1 centimeter on the diagram represents 8 centimeters in the ripple tank. Okay, so the question is, using measurements from figure 5.1, determine the wavelength of the wave in the deep water. Now, using measurements, meaning that we need to measure it ourselves. You need to have a scale with you during the exam, and you need to use the scale to make these measurements. So what you do is, by using these measurements, we need to determine the wavelength of the wave in deep water, meaning that we need to determine the wavelength. And now we know that these points, these lines are wavefronts. And as you all might know, that wavefronts are points that are lines that are obtained by joining the crests or troughs or any interface points on simultaneous waves. So if I had some waves like this, if I have a wave like this, and then there was another wave beneath it like this, and then there was another wave beneath it like this, and then another wave beneath it. So I could join all the interface points in these waves, or either they crests, and then I'll get wavefronts. So these are wavefronts. So from this we know that the distance between two consecutive wavefronts is the wavelength. And similarly, since these lines are the wavefronts, which are the lines I've drawn on the right with blue, so the distance between these lines would be my wavelength, and that's what I need to find using measurements. So I'll put my scale here and I'll find the measurements, and they'll give me an answer. They'll give me, let's say, for example, this measurement. I do this measurement and it comes out as, I don't know the exact answer because I'm using it on my OneNote, so I can't measure it properly. So and this, for example, comes out as 2 centimeters, let's say. So this came out as 2 centimeter, and then I need to use the scaling, which means that 1 centimeter on the diagram represents 8 centimeters on the ripple tank. So if this was 2 centimeters on the diagram, in a real ripple tank, it would represent 16 centimeters. So 16 centimeters, for example, would be, let's say, the wavelength of this wave, 16 centimeters. For example, I'm just doing this uh, on taking an assumption that it's 2 centimeters. When you have the question paper in front of you, you might know the exact value that would come. Okay, so the next part, calculate the speed of the wave in deep water. Now we just need to find the speed of wave in deep water. And for that, we know the formula that speed equals frequency times lambda, which is the wavelength. So speed equals frequency, which they've told us to be 3.6 hertz, times the wavelength, which is 0.16 meters. And from this, I'll get my answer. So I won't write it down. You all can calculate it yourselves. Okay, so the next part, the last part, as the wave passes into the shallow water, state what happens to number one, the frequency, number two, the speed. And this is a very important part. Like most people, or at least when I was doing my levels, I didn't know about this. So the idea is then when a wave travels from deep water to shallow water, Okay, so the frequency of a wave cannot change because the frequency of a wave always depends on the source. So once the source has oscillated and generated the wave, the frequency can no longer be changed. So the frequency of a wave, once it has been produced remains the same, and it cannot be altered whatsoever in any way. So that's what we know. What happens now is when a wave travels, and these waves require a medium to travel. Some waves are mechanical medium, which require a material medium to travel. Other waves are, for example, let's say electromagnetic waves, which require an electromagnetic spectrum. Some waves are gravitational waves, which require gravitational fields. And similarly, there are other type of waves which require other type of mediums. So whenever there's a change in medium, for example, mechanical waves require a material medium. So there was this shallow water and then there's this deep water. So whenever there's this change in medium, we go from deep to shallow water. The medium has a little bit been modified because first it was deep and now it's shallow. So what happens is its speed alters. Now speed is the thing which alters of a wave when there's this some alteration in the medium in which it's traveling. The frequency would always remain constant. So we come to the part that they've asked me what happens to the frequency, and I just tell them that the frequency remains constant. So the frequency remains constant. The next thing is speed, and this is keyword. The speed changes, and specifically when we go from deep water to shallow water, this speed decreases. The speed decreases, and the wave slows down. So the speed decreases and the speed has decreased, the wave has now slowed down. And similarly, if we go from a shallow wave to a deeper wave, from shallow water to deeper water, the speed would increase. And now, one thing which I would like to address here, we know the formula that speed equals frequency times wavelength. And I just told you that frequency is constant once the wave has been produced. So frequency is a constant. So from this, I know the relationship, which is that wave speed is directly proportional to wavelength. So whatever happens to my wave speed, whatever happens to my speed, similarly happens to my wavelength as well. So when the speed increases, the wavelength increases, and if the speed decreases, the wavelength also decreases. Now, one way to verify this could be is that I go and look at this diagram. So what happens in the diagram is that obviously I can tell this by simple observation that this length which I call it L1 is significantly greater than this length which I'm calling L2. So I just know that L1 is greater than L2, meaning that the wavelength in deep water is greater than the wavelength in shallow water. This is something which I just look by observation. And if the this is like just according to the theoretical results that if the speed decreases, so would the wavelength. So we kind of just verified this whole thing. So is this part clear to you? If anyone has any questions regarding this, feel free to ask it. Okay, so I'll assume no questions. And by the way, you can use your mic as well to ask questions if you want, or you can type them in the chat box as well. Next part shows a wave on the surface of water. The wave is traveling to the right. Describe what is meant by wave motion. So we just need to explain what wave motion is. So wave motion, or this term basically means to describe what a wave actually is. So wave is the propagation of energy from one point to another without the transfer of the medium itself. That's how you would define wave motion. Propagation of energy from one point to another. That'll get you the 1 mark. It's a 2 mark question, 1 plus 1. So propagation of energy from one point to another, that gives you 1 mark. Without the transfer of the medium itself, which is a very essential point, gives you the second mark. So this way you get both your marks. Draw an arrow to show the direction of movement of a water molecule at x. So we now need to draw an arrow to show the direction of movement of a water molecule. Now there are two things involved. One is the medium, or one are those particles which are constituting the wave. And then there's this direction of wave motion or energy transfer or propagation of wave. There are multiple ways to phrase it. So the wave is traveling to the right, but as we know in transverse waves, the movement of molecules is perpendicular to the direction of motion of the wave. So if the wave is traveling to the right, my water molecules would either be oscillating upwards or downwards. So that would be the motion. And now, obviously, if by observation I can tell that it's a crest, so obviously, if it's a crest, the molecule would obviously be moving downwards. They can't move any more up. So it's better to point it downwards, but if you point it upwards or downwards, that's correct according to the marking scheme, because the concern right now is whether it's upward or downwards or left to right. The next part, frequency of water wave and the wavelength. So by using these, they ask us to calculate the speed of the wave. So quite easy, you can do it yourselves. Speed equals uh, frequency times wavelength. The next part on figure 6.1, mark a distance which shows how far a wavefront at x moves in 1 second. Label this distance d. Mark a distance which shows how far a wavefront moves at x in 1 second. Label this distance d. Now we know the frequency of the wave. The frequency is 2 hertz. 2 hertz, a frequency of 2 hertz means 2 waves in a second, which means one wave takes 0.5 seconds. Okay, so the last line is not important for us right now, but this part is important. 2 waves in a second. Now they've asked me that how far a wavefront travels in 1 second. In 1 second, I know the number of waves formed would be 2. So there would be 2 waves formed. So the wave would move 2 waves to the right because 2 new waves will form and it moved 2 waves to the right. So I would know that in 1 second, this distance, how far x moves. So it will move a distance of 2 wavelengths, which would be this. So I should mark this distance and I would label this t. This would give me the answer. So I hope this part is clear to everyone. Okay, so similarly, another question, which is I think the continuation of the previous one. Oh no, that's entirely separate question. Okay, so cite one similarity and one difference of the two waves. So obviously, by quickly looking at it, one similarity would be that. Okay, so the one difference, first they've asked me about the difference. So one difference would be that both have different amplitudes and yeah, both have different amplitudes with them. So the difference in amplitude is a difference because this has an amplitude of, let's say, this much, and the other has an amplitude which is quite greater than that. Next, coming to the similarity. The similarity is obviously when it comes to similarity, first try to analyze these basic values. One would be frequency and the other would be the amplitude. One would be frequency, the other would be wavelength, another would be the amplitude A. Obviously, I can't tell the frequency, or I can, but for that I'll need the wavelength, so I'll just suffice with the wavelength. The wavelength of the first wave is 300 uh, sorry, the frequency or the time period. So I can't find the wavelength because I don't know the distance. So frequency could also tell me, another way to know the frequency could be through the time period. So the time period of this wave equals 300 milliseconds. So this is what I know. Then when I come to the next wave, I mark a whole wavelength. So the wave starts from here and the wave ends here. So it starts at 110 and the wave ends at 410. So this whole thing becomes equal to 300 meter per second. So that's the time period of the second wave. So both waves have the same time period. So a difference would be that they have different amplitudes, and a similarity would be that they have, I won't write the same time period. The difference is only supposed to be in three ways. It should either be in terms of frequency, in terms of wavelength, or in terms of the amplitude. So I can't say they have the same time period. Rather, I'm supposed to say that they have the same frequency. So that's how you answer this. The next part, The speed of water they've given us, determine the frequency, and we know this uh, to determine the frequency. I just found out the time period, so everyone we could just do this 1 over time period, and we get the frequency. The next part, the wavelength of wave p. So for the wavelength, I could just simply use the formula speed over frequency equals wavelength. So by using this formula, I'll get 2 divided by whatever frequency I just found in the previous part, and that'll give me my wavelength, which I think would be something around uh, 0.6 meters, I think, but you can verify it yourselves. Okay, so these were some questions regarding waves, and one of the very important stuff that we need to know that whenever there's a change in the medium of the wave, its speed changes. Speed is the only quantity that changes. Frequency remains constant, speed changes. And due to the frequency remaining constant and speed changing, there's a change in wavelength of the wave as well. So the wavelength of the change in wavelength is not something that came about by itself. Rather, it came about a result of frequency being constant and the speed decreasing. So that's what we know. The next part, a lamp is positioned at the bottom of a small pool of water. The critical angle for light passing from water into air is 49 degrees. Explain what is meant by the term critical angle. So the term critical angle, you all know, is critical angle is the angle of incidence for which angle of reflection equals 90 degrees. So that's how we define critical angle. Or you could say you can't, instead of saying 90 degrees, you could say the angle of reflection is perpendicular to the normal or stuff like that. That's the same thing. Okay, so now we know that the critical angle is 49 degrees, and 49 degrees meaning that whenever the angle of incidence would be greater than 45 degrees, uh, they would be total internal reflection. So obviously they've now shown me 3 waves, and they're asking me about the path of all these 3 waves. So the first wave, which goes vertically upwards, it makes an angle of 90 degrees, or sorry, angle of 0 degrees with the normal. And we know that this is a very special type of case where the angle is 0 with the normal. In this case, there is no reflection that takes place. So the object just easily travels into the other medium without any reflection. So it goes straight. The next wave is it makes an angle of 60 degrees, like not a angle of 60 degrees, but the second wave. Okay, so this would be the surface where the medium changes, and we need to make a normal to this surface. So this is how we make a normal, and I just remove this part. Okay, so I need to find this angle, and this angle, which is the angle of incidence. So if this angle of incidence turns out to be greater than 49, it means that there would be total internal reflection. But if it turns out to be lesser than 49, the light would just reflect into the other medium. So now I need to find this angle. And these type of questions require some knowledge of mathematics or angle math as well, where you apply those angle properties and find the angles. So a simpler way to do this could be, I know this is a triangle and I know this angle to be equal to 60. And I know this to be equal to 90. So if it's a right angle triangle, this angle green should is only be equal to 30 degrees. So since it is supposed to be equal to 30 degrees, it is lesser than the angle of its angle that it is lesser than the critical angle, so reflection takes place and it moves to the other medium. So and now since it's moving from water to air, meaning a denser medium to a less denser medium, the ray of light would move away from the normal. So the path of the light should be something like this. It should be away from the normal, or in other words, the angle of reflection must be greater than the angle of incidence. Okay, so this is how we do this part, and then for the next part, similarly, I draw a normal, and then I complete this. I know this angle, it's equal to 30. degrees. So obviously this angle, which is the angle of incidence, is supposed to be equal to 60. And since it is greater than 49 degrees, greater than the critical angle, total internal reflection takes place, and it reflects about an angle of 30 degree in this direction somewhere, 60 degrees. So what they've asked me is to draw the path taken by each ray after they strike the surface of the water. I don't need to continue this wave any further. In other questions, they might sometimes ask you to continue this wave. Like, tell me what happens to the wave. Does it travel out of the water or does it internally reflects again? But right now, that's not what they're asking me. So that's not what I'll be answering them. The next question, similarly, explain what is meant by critical angle. And the next part, calculate the refractive index of diamond. So the refractive index of diamond, the formula is n equals 1 over sine c. So that's my formula, and I'll just simply use this formula. I know the critical angle, which is 24, and using that, I'll just simply find the refractive index, which is n. So I hope this part is again clear to everyone. Okay, so the next part shows two diamonds of different shapes. A ray of light enters each diamond as shown. Continue the path of each ray until it emerges into air. So in the previous part, they just asked me to like draw the path of ray after it strikes the surface, and the next this part they're asking me to continue it until it emerges into air. So I now need to complete it until it travels back into air. And this part is also something very simple. And the only trick in this is to find the angles. So to find the angles, what I'm supposed to do is for the first part, I'll first need to make this normal with the surface. So I just do that. I make a normal with the surface. So I get this normal. And obviously my angle of incidence would be the angle which it makes with the normal. So this is obviously supposed to be 20 degrees because the normal makes an angle of 90 degree with this. So I just simply know this. We use lighter pen. So I know this would be equal to 20 degrees because this whole thing is 90 degrees, and if this is 70, the remaining of it should be equal to 20. So this is, I know it's equal to 20, and this 20 is lesser than the critical angle. The critical angle is 24 and it's less than that. So obviously there would be no internal reflection and it would just simply pass into air with, and obviously since it's traveling from diamond into air, so it would move away from the normal. So it would move somewhere like here with this angle which should be greater than 20 degrees, or should be greater than 20 degrees. And similarly, the next part, I draw again a normal here. So this is my normal. And obviously I know that this whole angle is supposed to be 90. And if the first part is 45, the remaining part should also be 45. So this angle would be equal to 45 degrees. And if it's 45, so I now obviously know that it's greater than the angle of incidence, the critical angle, meaning that the light would internally reflect. Internal reflection meaning that it would reflect at an angle of 45 degrees. So now here I'll again draw the angle, and again, obviously I know if I like extend these lines and make this circle, so this is 90 degree, 90 degree, and this angle would again be equal to 45. So it's again making an angle of 45, and now there would again be internal reflection. So this light would now again internally reflect and now go upwards. And since it's now making an angle of 90 degree, so there would be no reflection and it would just simply pass on from this in this direction like this. So this is how I complete this part. Okay, so here we'll take a 10 minutes break for Isha. So I need to head to the masjid and I'll be back and then we'll continue inshallah. Assalamu alaikum. So let's proceed where we left off. So we did this question, and now the next question is a bit similar. I won't be solving it, but I'll just do like outline what's required to solve it properly. So light enters a parallel-sided glass block at A. The angle between the side of the block and the ray of light in air is 35 degrees. The question goes on. They're just explaining this diagram. Calculate the refractive index for light in the glass. So obviously we know the formula for refractive index. N equals sine I over sine R. So obviously we use this, and we're just able to find N, and that's the refractive index. And then they're asking me about state one condition necessary for total internal reflection to occur. So one condition which is necessary. Obviously, one of the thing is that the critical angle must be the angle of incidence must be greater than the critical angle. So that's something aside. But one condition which is very necessary. So like without which the concept of internal reflection is not even valid. So that type of a condition is that the light or the ray must be traveling from a denser medium to a less denser medium, because if it's the other way around, because if it's from a less dense medium like air into glass, a denser medium, so there would never be internal reflection. There would always be reflection, because light would obviously always be moved towards the normal. So one of the conditions necessary is that it necessarily be from a denser medium to a less dense medium, for example glass to air, then total internal reflection could occur. So next part, continue the ray to show the path of light after the total internal reflection at B and until it leaves the block. So they've told me that there is internal reflection at B. So obviously I'll just draw the diagram accordingly. I know these values. I just make a triangle. The best way to solve this question is make a triangle. So this is 90, this is 33. So obviously this angle, the angle of incidence is supposed to be equal to what? Uh, 57. 57 degrees is what it's supposed to be equal to. So this is 57 degrees, and this is also supposed to be 57 degrees. So 57, 57, it goes on obviously, and now till it reaches a point here, and then obviously it reflects and goes out of the block, out of the glass block. So something like this, I make a normal, and then all I need to show is that after once it goes into air, it will move away from the normal. So that's something I'll need to show. That's how I get my marks. Okay, so I hope this part was clear to everyone. Because similarly, we have similar questions again and again, which would be repeating themselves. So I won't be going into the details of all of them, because we've like understood what the actual theory or the required stuff is. So the question is, as light enters the glass, state the speed of light in air. So we know the speed of light in air, which is equal to 3 times 10 to the power 8 meter per second. As the light enters the glass, state what happens to the speed of light, the frequency of light, and the wavelength of light. So obviously, I've told this earlier that the frequency of light can never change, because once the wave has been produced, the frequency does not change. It only depends on the source or on the oscillation of the source. So once the source has oscillated and has produced the wave, the frequency of the wave can never change. The next thing is speed of light. What happens to it? Previously, one of the questions we did was water waves, and they moved from deep water to shallow water. In that case, their speed decreases. Obviously, there was a little bit change in the medium, so the speed decreases. Similarly, although electromagnetic waves do not require a material medium, but when they when the wave does move from a less dense medium to a denser medium, there is some effect on the electromagnetic spectrum. So because of that, there is some change in the speed of the wave, and the change is such that whenever light goes from uh, a less dense medium to a denser medium, as the density of the medium increases, as the density of the material medium increases, the speed of the electromagnetic wave slows down, decreases. The speed decreases and the electromagnetic wave slows down. So as light enters the glass, what happens to the speed of light? Glass is obviously denser than air, so the speed of light decreases. And obviously, if speed has decreased, so would the wavelength. And then the next part, mark and label the angle of incidence and the angle of reflection. So obviously, angle of incidence would be this angle I, and angle of reflection would be this angle R. A ray of blue light strikes the surface of a glass block at an angle of incidence of 89 degrees. Calculate the angle of reflection of the light in the block. So we just need to find the angle of reflection. We know n, so we do know this formula: n equals sine I over sine R. So similarly, we do know that 1.5 equals sine 89 divided by sine R. So from this, we'll be able to find R. And R, I think, comes out to be something around, I just remember this part, R comes out to be something around approximately, I think, 43 degrees. So that's why they're asking me in the next part, explain why the angle of reflection of blue light in glass is always less than 45 degrees. So for an angle of incidence of 89 degrees, the angle of reflection was 43. And we can't increase the angle of incidence any more than 89, because once we do it 90, the light will just simply pass off from the edge. Like there won't be any reflection or any passing through, like light won't pass into the other medium. It won't go from air to the glass if the angle is 90. So the angle cannot be increased beyond 89 degrees. And at an angle of 89, the angle of reflection is 43. And as we know, if I decrease the angle of incidence, the angle of reflection would also decrease. So similarly, if I, let's say, move the angle of incidence and make it 80 degrees, so the angle of reflection would now be, let's say, around 60 degrees. So angle of reflection would be becoming lesser and lesser. Sorry, not 60. Uh, if at 80 degrees, 89 degrees angle, if at an angle of incidence of 89 degrees, the angle of reflection is 43. Anything beneath this, if I go anything lower than this, 80, 60, 70, something, so the angle of reflection would be lesser than 43. So that's how I explain this part. That's what they're asking me. Why is the angle of reflection always less than 45? So I just tell them that the angle of incidence cannot go beyond 89. So obviously it cannot go beyond it, but it can go less than it. So whenever it goes less than 89, the angle of reflection would go less than 43, and therefore it would always remain less than 45 degrees. That's how I answer this. And then this blue light traveling in air strikes the side of a different glass block and continues in the same direction as it enters the glass block. shows a ray of light in the shape of the glass block. The critical angle for this glass is 42 degrees. I just now need to complete this diagram. So I know the angle of reflection is 42 degrees. So I first draw, the very first thing would be to draw a normal, and I'm using this red pen always, and I'll be always using it for angle of reflection, for the normal. So I draw a line here. This would be my normal. This is my normal, and this would be my angle of incidence. I need to find I. How do I do that? That's like the part, which is that's what I need to find. Okay, so what they've told me in the question is that this angle is 45 degrees. This angle is 45 degrees. So from this, if I apply the Z property of angles, or a similar type of property which states that, or if I just even observe this diagram, so it tells me that this angle is 90 degrees. So if it is 90 degrees, then obviously by the total angles in a triangle are supposed to be 180 degrees, and this is obviously supposed to be 45 degrees. And if it's supposed to be 45, this angle of incidence here is supposed to be equal to 45 degrees. So this is what it's supposed to be equal to. And if it's 45 degrees, it's greater than the critical angle, which is 42. So there would be total internal reflection, and it would move back. And then it would come somewhere here, strike some point here. And again, at this point, if I apply all these things, this is 45. So the same things would apply. And the angle of angle to the normal here, this angle, just a second. This would be my light ray, and again the angle which it makes with the normal here would be equal to 45. I'll just the same reasoning would apply, and then there would again be internal reflection, and it would move at somewhere here. And this time, obviously, I can see, look, tell this by observation, that the angle of incidence would be something less than 45. Like, this is some basic observation, and you could apply the same reasoning and find it out as well, that this time it would be less than 45. So the line would simply pass by reflection. So it would be something like this. And this is just, I'm just drawing it to scale. There's a possibility, and I think that's when that one is the correct part. If you use a protector, you'll realize that the line is going directly like this. So it's just supposed to simply straight pass on. So this is how actually it goes. So this is how it becomes. So that's what they've asked us. Complete the path of light until it leaves the class. So that's what I've done. And initially, the first part is explain why the light continues in the same direction as it enters the glass block. Why did it continue in the same direction? Why was there no reflection? The reason is the angle of incidence was 90 degrees, and when the angle of 0 degrees, and when the angle of incidence is 0 degrees, there is no reflection. The light just simply passes on. Okay, so that was the previous questions. Now moving on, there's just 2-3 questions remaining. So state the angle, say the name of angle of incidence marked 41 degrees. So angle of incidence marked 41 degrees is the angle at which the light goes in this direction, and there's a weak reflected ray coming back. So this angle is obviously what we call as the critical angle. So that's what I just simply write. And then the next part is rays of light are incident at B with different angle of incidence. On figure 5.2, the angle I1 is less than 41 degrees. So it's less than the angle of incidence, and it's less than the critical angle. So I need to complete the path of ray. So obviously, if it's less than the angle of incidence, light will simply pass on into air, and this is how it would go. The next part, where the angle of of incidence I2 is greater than 41 degrees, which is figure 5.2b. So obviously, if it's greater than 41 degrees, it's greater than the angle of the critical angle. So obviously, there would be internal reflection and light would go out like this. And now the next part, they've given me the speed of light in the glass block and the diameter of the glass block. They've given that as well. So they've given the distance and they've also given the speed. So I just need to find the time. So I know the formula, speed equals distance over time. From that, I just get my answer. And by the way, yeah, the diameter of the glass block. So this point is A and this point is B. So this line is not equal to the diameter, rather it's equal to the radius. So what I do is I this distance here should be half of the diameter, which should be 0.05 divided by time equals 2 times 10 to the power 8. So this is how I'm supposed to find t, and that's how I'll get the answer. So moving on to the next part. This is again a similar question, but there's some things they've asked which I would like to address. Explain why the light ray does not change direction at P. Why does it pass directly into the glass block and does not change direction at P? So the reason is again that the angle of incidence is zero. So that's why there is no reflection that takes place. And how is the angle of incidence zero? So for that, and this is something important, I first need to identify the normal or the surface where the glass block and where the surface between the air and glass. So for that, this is the surface, and to find the normal to the surface, I first make a tangent to the surface. So I would draw a tangent to the surface, which would be something like this. And then I would draw a normal to this surface, which would be something in this direction. So obviously, the white light is making an angle of 0 with the normal. So the angle of incidence is 0. Therefore, no reflection takes place. And why explain why no light passes out of glass at Q? So obviously, if no light is passing out at Q, it means that internal reflection is taking place. So internal reflection is taking place, and why would it be taking place? So it would only be taking place when the critical angle, where the angle of incidence must be is greater than the critical angle. So there is no uh, light wave passing out of the glass at Q. Draw the complete path followed by this ray. So they've told me that internal reflection takes place. So I draw a line like this, where this angle is again equal to theta, same as the angle of the ray when it struck Q. The student directs the white light into the glass along different paths so that the angle theta is slowly reduced. So the student is now reducing theta. Explain what happens to the ray at Q. So what happens to the ray at Q? If it's reducing the angle, there would eventually come a point where the angle of incidence would now be lesser than the critical angle. So at this point, there would be reflection taking place. And what we'll observe at Q is we would observe some light at Q. We would observe some light at Q. So that's what you need to answer. So this is it. And now the next part is, which would be last question for today, which is one ray of light is totally internally reflected at the boundary between water and air. On figure 3.1, mark the critical angle and label it C. So I need to mark the critical angle. First, I need to realize at which of these, they've drawn three rays. So which of these rays have an angle of incidence such that the angle of reflection is 90. So that is only the case with this this ray. So this would be my angle, which would be the angle of incidence such that the angle of reflection is 90. So this I would label as C. This is the critical angle. Now the refractive index for water. So I need to find the refractive index for water, and I know the formula for this. The formula is simply n equals 1 over sine c. So if I do this, if I apply this formula, I know sine c, I know this whole thing. So I'll just simply be able to find n. So that's how I do it. So for that, a way to find that could be either I do this, and but the problem here right now is I don't know c, so I can't apply this formula though it's valid. The next thing would be to I can use values from here, but here but where the trick is involved, I can't just simply say that n equals sine I over sine r. I can't say this, and obviously for the formula is this, but I can't do that the n for water is equal to sine 25 over sine 34. This would be incorrect. The reason why this would be incorrect is that the refractive index, the angle of incidence, the angle of refraction is supposed to be in the medium of which we're calculating the angle of reflection. So for this, uh, or to explain this in other words, what's supposed to happen is that the light, the angle of incidence must not be formed in the medium of whose refractive index we need to find. So if I need to find the refractive index of water, the angle of incidence must not be forming in water. The angle of reflection should be in water. The angle of incidence should be in air on in whatever other medium there was. The angle of reflection should be in water if I need to find the refractive index of water. So what I do is I reverse this ray. So I assume that the direction of ray was as if it's going from air into water. So obviously we know this that the angles would remain the same. So I assume that it's kind of happening something like this. So now what I do is n of water should be equal to sine 34 divided by sine 25. When I do this, that's when I get the correct answer. The reason that the angle of refraction should be uh, in that medium whose refractive index we need to find. So we need to find the refractive index of water. So the angle of refraction should be in water. So that's how we do this. The critical angle for the boundary between water and air. So once we find n, we were able to find n. So we could put n here and we could just simply find c. So that's how we do this part. So I hope everything was clear. So if any of you have any questions, feel free to ask. Otherwise, we'll end the class for today here. Okay, so I guess no questions. So then let's end the class and hopefully we'll meet inshallah tomorrow. Or obviously the day after tomorrow on Monday, inshallah.